Yeah, yeah, you missed that also.
You want this?
Yeah. So powerful
Okay, let's start class. I'll put this here. Okay, so in our class today, or in this semester, we're going to learn about the design of a computer system.
Do we have these slides?
These slides are on Moodle. You can download them and write to them if you want. If you want to have a, want to annotate them, it's probably a good idea. So we're going to learn mostly about the how to design a computer, which means what are the parts of the computer. It's in that sense, the course is a continuation of the course that you did in digital systems. So you learned there how to build like a full adder and various things we learned how to build. Now we're going to take those pieces and view them as like building blocks to build a computer out of them. But in a diagram, we're going to learn how to diagram a computer and how to understand a particular architecture as our example. So our example will be a computer called a MIPS, MIPS, which is particular chip. It's simpler than the Pentium that you have in your computers or whatever, or the AMD that you have in your computer. So that's why it's good in school to learn to use that one.
Which is MIPS stand for?
We'll see. So okay, let me skip this. For the
How
lab.
many minutes will assemble?
What is an assembly language? First of all, so this is actually I combine kind of the lecture for the lab where we do assembly programming, and I give you a little introduction to that here also because there's an overlap in the beginning of the course because I have to teach you about commands. Did you actually have the lab already?
Yeah.
Who
is the dude that teaches?
Avi Treisman?
Yeah.
Avi Treisman.
Brother, you didn't explain a thing.
Okay. Well, he didn't use my slides. Did he use any slides?
Well,
for like the last 10 minutes.
Okay.
What is the role in department?
What?
What is the official role in the department?
Official?
Official role in the department?
Mine?
No, his.
What?
So the chance of assessment.
Treisman teacher.
You guys are both like.
the problem is he ain't got your slides.
He doesn't have my slides.
There it is.
I made these slides. Took me 2 years. There you go.
Whoa.
I mean, I made them over the course of the year. Okay, so what is an assembly language? So first of all, I need to explain to you some basic ideas, which is that you guys learned how to program in C. C is considered a high-level language.
Not according to
And what
him.
high-level?
He said mid-tier. He said very punctually mid-tier.
Don't interrupt.
No, I don't. Just telling you what he said.
Okay.
Wikipedia C is the high level language.
It is, I'm going to say what I believe, but people believe. C is a high-level language. What we mean by high level, we mean it's far away from the hardware. The hardware is actually built to understand certain instructions, and those instructions there's a set of those instructions, and they're called the chip set because of the set of instructions that the chip understands. It's also called machine language. If we were writing that language, it would mean writing it like this in ones and zeros. In other words, the machine only understands on and off, doesn't understand anything else. When you write in a high-level language, ultimately it gets compiled and translated into the machine level language so that the computer can understand it. Why is C++ a high-level language? Because I can write in C++ and compile it for a Macintosh, and it'll have a certain set of ones and zeros. And if I compile the same C++ code for a Intel machine, then it'll have a different set of ones and zeros, but they'll both achieve the same results. So I can write in C++ and for any machine that way, as long as I have a compiler for the particular machine I want to run it on. When I write in assembly, I'm writing for a particular chip. And therefore I have to learn, when a person creates a chip, he actually publishes a manual of what are the commands for that chip. So that is called the chipset. Assembly language is, sorry, the ones and zeros are like machine language. Let's call that machine language. So assembly language is a step in the middle, which is a one-to-one correspondence between the ones and zeros that the machine understands and English. But it's not a high-level language. Assembly language is a low-level language because it's directly connected to the hardware. The assembly for one chip will be different from the assembly for another chip. So if a person says, I know assembly, he doesn't really understand what he's saying. You can't know assembly. You can know assembly for a particular chip. Each chip has its own assembly. On the other hand, all the assemblies are similar. So you could kind of say, I know generally assembly.
Especially if he knows for a lot of different chipsets.
If he knows for every single chipset, yeah, then maybe he's assembly. There is one, all right, so now we go on. When were assembly languages first invented? So the first computers did not have any kind of programming. They were more akin to a handheld calculator, which means a calculator, think about it, you can't program it. I mean, complex calculators you can, but a regular simple computer calculator, you just press the plus and it does plus. You press the minus, it does minus. All the functionality is right there as a button. It's not programmable. And you can build such a thing with logic circuits that you learned in your logic systems course, your digital system. Now, the first programmable computers were invented around 1944. That was the first one called Mark I. The actual name was this automatic sequence controlled calculator. So they called it a calculator, but it was controllable. So it was programmable. And that computer was used in the Manhattan Project to build the first atomic bomb. There were other programmable computers around the same time, 1946, as ENIAC, and there was this EDSAC also in 1949. Now,
Grace Hopper.
Grace Hopper. I like to talk about Grace Hopper.
What a name.
Somehow it seems like only.
Not Grasshopper. Yeah.
No, I know, it's-
Was developed by, like,
So it's something they called her actually Amazing Grace Hopper. Grace Hopper was a professor of math, and when World War II started, she volunteered for the U.S. Navy. And as a math professor, they sent her to the division that dealt with computers when they had computers for, let's say, missile systems and calculating trajectories. So she came there and she saw them programming in ones and zeros, and she said, this is too complicated or too inconvenient, too hard to remember all these ones and zeros. And the men there all said, what do you mean? There's no problem. We don't remember those ones and zeros. She said, well, I'm going to make your life easier. I am going to write the first assembler. She came up with the idea, nobody had thought of this idea, of writing in English and then having a separate program to translate it into the ones and zeros. So she invented that idea, which is a major leap forward in programming because it made programming much easier. She also did the one more thing, which was she invented the first high-level language. She said, all these assemblies are focused on one particular machine. I have to write assembly for each different machine. Let me write a compiler which can translate from a high-level language to any machine. And of course, she has to write it. First, people understand that every single computer needs its own compiler. It's not like there's one such thing as a C++ compiler. There's a C++ compiler for an Apple, and there's a C++ compiler for an Intel machine, and they're different. You have to write for each new hardware that comes along a compiler. But the point is, she came up with the idea of writing in a language which is not connected at all to the assembly. In fact, one line of C++ might be several lines of assembly in one computer, and might be only one line in another computer. That's called abstraction. She abstracted away from the hardware and came up with a high-level language, which is what we call machine independent. It's independent from which particular machine I'm writing on. The first one was COBOL, and it's still in use, as far as I know, by some banks because there's old codes. What?
It's still whatever, Cobalt 14 or whatever.
Yes.
You know.
Right, because they have old programs. It's cheap. It's simpler to just keep updating them than to write it all together. Okay. What are the characteristics of assembly? So as I said, there's a small set of commands that each chip can understand. You build your program out of that. The assembly translates a human type version of machine language into proper machine language. Why should we learn and use assembly? So assembly gives us complete control over the final machine code. What I mean by that is the compiler can compile your code in an inefficient way. It can come up, you can write one line and it can be a badly written compiler, let's say, and write 10 lines. Or it doesn't know exactly what your intentions are, so it has to make 10 lines because it doesn't know where you're going. It translates the line, it doesn't know what the next line is. So it doesn't know exactly where you're going. So it may end up with inefficient code. If you write directly in assembly, you control exactly how many lines it is, and you can write therefore code that is faster. And this is going to be crucial in certain circumstances like a car's autopilot, which has to, make quick changes as a person runs across the road in front of you, has to quickly notice that and stop. You want the code to be running fast. Also, if you're doing high frequency trading in the stock market, you want things to go in the millionths of a second. So you want your program to run fast. And the third reason I give is that just to be professional and to know you should know what you're doing. So you can't just write in this high level language and have no idea what's actually happening. So if you want to really understand your field, you should know also what's going on at a lower level. Yes, question.
Higher level languages like C also let you put assembly in them, right?
Yes, you can write like ASMs and then tell this is assembly, but then you have to know which machine you're on. Right, you can insert all 2 lines of assembly in your high level.
I have a suspicion that the examples you gave are not going to write the whole thing in assembly.
We're going to write the whole thing in assembly. We're starting from scratch.
No, I'm saying they're not going to write a whole high frequency trading thing. In
Oh, that a high frequency trading, right? You may have parts of it in assembly. Yes. Okay, so you asked actually what does MIPS stand for? It stands for microprocessor without interlocked pipeline stages. If you wanted to know, you don't have to remember that.
That's not even shorter.
But
so much better when they
we call it MIPS. It's a particular computer. Yeah, it's like a little chip. It's used in various devices. Like it's actually used in some Tesla cars. The parts of their computer systems are run on that chip, and then it's programmed.
You're saying Elon Musk is opening like MIPS on his computer? He's just like, I'm Elon Musk right now.
Well, I'll say like this: if you understand, if you want to work for Mobileye, you certainly could work in their assembly division. Now, there's certainly people that program MIPS in Mobileye, which is a multi-billion-dollar, which was sold, for $15 billion.
Wow.
So you can make a lot of money in assembly. You don't have to know
Code by line.
The book for this course that we're going to be using is Computer Organization and Design by Patterson and Hennessy. There's several copies in the library. They're different editions. It doesn't really matter which edition you have, in my opinion. They're all, there's only slight changes between them.
Yeah, I feel like knowledge it's not like
Doesn't change that much.
it's not like the fourth
Okay,
edition.
so let's get right to assembly. And here's an example where you see I have
Oh my God.
A,
You're
B,
explaining. Also explain things. Should you explain it differently?
A equals B plus C. I translated this example is from the book, but I translated it from pseudocode into C++ because I assume you know C++. A equals B plus C is a perfectly nice line of code. And how would you do that assembly? You would write add A, B, C, where A, this order here is important. A is the target, I'll call it the target, and BC are the 2 operands that I add together and put in the target. Similarly, sub D equals A minus E, so I would write it like that.
I mean, don't you have to like pull into the register?
Yes, we're not, I'm teaching you slowly, which means that this example is pseudo assembly. We'll get to proper assembly soon. Now, what if I want to do a complex C program, C line, like this? F equals G plus H minus I plus J. That's more complicated. It's 1 line in C++. In assembly, it's going to be 3 lines.
That's it.
Because I don't have any parentheses. No such thing as parentheses. I just have add. So what am I going to do? I'm going to add G and H and temporarily put them into T0. We'll call the variable T0. It's actually, we're going to learn that it's not a variable. It's a register. It's something called a register, which you did talk about in your other course in digital systems. And you build a register out of what? Who knows what you build a register out of? Flip-flops. So you can build a register. The point of a register is that you can store data in it. It won't just go away. It'll sit there. So I have to use a register. These also should be registers, but this is pseudo assembly. So for now, I'll just write them as G and H. So G and H are going into temporary register T0. That's why it's T for T temporary. I and J are going to temporary register 1. And now I've got this value and this value stored, so I can subtract them and put the final value in F, which is what I wanted to do. So you see that the compiler would look at this code and create those 3 lines. Of course, it could do it differently. It could do all kinds of silly things, like it could put G into a register, and then put H. It could do extra lines that don't give me the wrong result, but take more time. Because the compiler doesn't always know exactly what your intentions are. So now let's talk about registers again.
Do we need to know how registers work exactly and how do they save information?
No, that was your previous course.
Yeah.
In your previous course,
Yeah.
you learned
We did.
how registers work. You passed that exam. You know that.
Hell yeah.
I'm not going to test you on that again. Unlike high-level language, MIPS has a finite set of variables. Why is a finite set of variables? Because they're not really variables, they're registers. And the computer that means they're built physically in the computer there, and there are 32 of them. And that's all you got. You have 32 places to store data and to manipulate that. Now, each register, not only are there 32 registers, but each register in MIPS is 32 bits long because it's a 32-bit architecture. If your computer at home is a 64-bit architecture, guess how big your registers are? Twice that size. They're 64 bits. That's what it means. That you have a 64-bit architecture means your registers are 64-bit.
But isn't it 64 by 64 instead of 32 by 32?
It doesn't have to be. The number of registers doesn't have to be 32. It's convenient for it to be 32. But it could be less, and it could be could it be more? It could theoretically be more, but it's not. It works out conveniently to be the same. It could be, I don't know, on a 64-bit machine, it could be that there's 64 registers. It doesn't logically have to be. If each register is 32 bits long, then it's 4 bytes long, because a byte is 8 bits. This is one of my 4 things that you have to remember your whole life. One of them is that a byte is 8 bits.
What are the other?
Very useful. The other ones I'll talk about, but
Things are gonna happen.
no, it's very useful in this course and in other courses to know that a byte is 8 bits. So therefore, a register is 32 bits long. That means it's 4 bytes long, and we call that a word. So we say word length. We can say the word length on MIPS. This is all I'm talking about MIPS now. There's another machine could be different, but on MIPS, the word length is 4 bytes.
MIPS is an example of this chipset with this
MIPS
specific
is
assembly
this,
language.
yes.
Okay,
In
thank you.
other words, we're learning the architecture of MIPS as a paradigm, as an example, as a simple example of a computer. The truth is, if this course would be based on a different chip, then we would discuss that. We could have a course where we discussed a chip that was 64 bits. Then it would be different. Okay, so how much different would it be? It would be different in many ways. How much is a very strange question.
11.
Yeah.
14.
You want to say it would be like entirely different, or just like a few things and take care of the
A
number?
few things would be different here and there. Okay, why are there so few registers? So first of all, registers are expensive. So we don't want to just like throw at our machine hundreds and hundreds of registers. Makes it more expensive. We want to keep the prices low. Secondly, smaller is faster. The more registers we have to sort of navigate to get to them all. And it makes that processing slower.
Defeating the whole purpose of why we're doing so.
And we're right, we're trying to have, the computer wants to be fast. Yeah.
32-bit processor has 32 registers, 64, 64. Oh,
So we could say that, but it doesn't have to be that way.
Okay.
It's also way
64,
from
well, a
register.
64-bit machine means that the size of the register is 64 bits.
Oh, that's.
It doesn't mean how many there are.
Got it. So that prefers how much.
It also means that the memory space is 2 to the, it possibly can address 2 to the physical memory could be up to 2 to the 64. Instead of 2 to the 32. That's also what it is.
Oh,
In general, in this course, our favorite number is 32 because we're going to have 32 registers. They're each 32 bits long, which is 4 bytes. And we can refer to each register by its number or its name. The numbers are obviously going to be 0 through 31. Okay, so let's now the third thing is that the actual translation of the command into ones and zeros. Remember I said that a command will be ones and zeros? How many ones and zeros? So all commands are the same length. They're all 32-bit commands. So we actually can fit a whole command exactly into a register. Is that the same size? If we wanted to put if we want to put a command into a register, we could. Yeah.
What does that mean, put a command, like put the value that resulted from the command, or?
No, the command itself. For example, we have this add here, add t. This will be translated by the assembler into ones and zeros, this whole line here. And how many ones and zeros? 32. This line will also be commanded. These are each commands, or actually more properly called instructions.
Why would we want to put that into a register?
You could really.
Well, we wouldn't really. We wouldn't do it.
Instruction is a
We
bit,
could. I'm just saying that I'm just pointing out that the lengths are the same.
the instruction is a bit, and then all three addresses are each a bit. A byte, sorry, it's the instructions a byte, and then each three addresses are a byte, so that's the whole word.
No.
Cause the,
I'm not gonna, I'll explain later how exactly it fits into 30.
cause it's four, it's.
I'll
8, 8,
explain
8.
later. Don't rush. I'm going fast enough. So that's why this is the whole slide here, because it's an important point. Commands are also 32 bits. We'll see how you break a command down and give it to its parts that are 30 bits long. I mean, I'm thinking about the, do we put, there is something called the instruction in the design of the computer. Back to your question about why would we want to put it into a register? There is a particular register, not of these 32. There are other registers. One of them is called the instruction register, and it's 32 bits long also. And we do put the command there. So there is a register specifically for putting the instruction into it, because the computer can't read the instruction until it's in a register. So we do put it in. I mean, I mean, we don't do it as a programmer. We don't do it. The machine does it. Okay, so
Puts
let's
it
go
into
back
one of
to examples of assembly.
It puts the command in one of the 32 registers.
No, there's there's a special, there's some extra registers
33rd
that you don't have access to directly, that the computer uses for its own purposes. And one of them is called the IR, the instruction register, and we'll learn about it. And
Okay.
the actual instruction will go into that register to be accessed.
I feel like that's a fun register to access it again.
Okay, so now let's look at another command, even a more complicated. Notice it's a single line of C++. It's going to be 3 lines of assembly. Did we do this one before?
Yes.
Why?
Added in data.
Oh, but I'm correcting it because, see, I say the
Register that.
correct version, because you can't really say G and H. There's no such meaning to that. So I'm saying, let's assume that G, H, I, and J are in S0, S1, S2, and S3. Notice I put a dollar. Always we put a dollar before the register name or number. That's just a programming convention. I mean, it has to be done. If you don't write that, it won't compile. Actually, in some programming languages, they still have a dollar in front of your variable name. So if you have a variable name called counter, you don't just write counter, you write dollar counter. And the reason they do that is because the people who wrote it were used to writing in assembly. It's a convention that was adopted from assembly. So again, what we do is the same thing. The G and our H are really the S0 and S1. So I add them S0 and S1, put it into T0, the S2, S3, put it into T1, and then I subtract and put it into T4, into S4. So that's the correct version of the translation of that command. But what if we want to store more data than just 32 pieces of data? We might have an array. Our array might have hundreds of pieces of data. Where are we going to store that? 32 registers is not enough. We store this in the memory of the computer, not in registers, it's something else. It's called the memory of the computer. And there we have the full access to all the memory of the computer, all the RAM of the computer, which could be 4 gigabytes. In fact, that's the maximum size it would be on this machine, 4 gigabytes. So we'd have a lot of space to put our arrays. And then what will we have to do if we want to manipulate that data? In this particular architecture, we cannot directly manipulate it in memory. We have to manipulate it in the registers. The registers is where we have to manipulate it.
But how do we store it? I mean, how do, like, with our 32 registers, how are we able to make one of those registers kilo an array?
we'll get to it slowly. It's a little bit complicated, so I'm gonna get to it slowly. That's exactly what I'm gonna do in these slides.
Basically, later, we're gonna find a way to have information across multiple registers.
So for example, I'm gonna look, for example, imagine it's already in memory. I need to load it into a register. So we have a command, special command called loading, or we'll see it, LD, LW, load word, loads a word into memory. Sorry, from memory into a register. And I'm gonna give you a mashal for this. In a hospital, a metaphor. In a hospital, you have many rooms where people sleep, and you maybe only have a smaller number of surgical rooms. Like you maybe have surgical theaters, I think they're called, like 16 surgical rooms you'll have. And what's special about those rooms? Oh, they have very bright lights, and they have all kinds of monitors, and they're very clean. And that's where you do surgery. You don't, when a patient needs to have surgery, they wheel him into the surgical room, do the surgery, and then wheel him back into the sleeping room. It could be into a different sleeping room, could be the same sleeping room, but they do all the procedures in the surgical room. There are 16 of those surgical rooms in a hospital, let's say. In our MIPS, there are 32 registers. Those are like 32 surgical rooms. In those registers, once the data is in the registers, we can now do surgery on it. We can add it, subtract it, we can do, but we don't want to put in every single sleeping room all the equipment for surgery. It'd be very expensive. We wouldn't want to have all that stuff in every single room. So we can figure out how many surgical rooms we need, and then we can build as many sleeping rooms as we want. So that's exactly that's a mashal to understand the relationship between memory and registers. Memory is very big, lots of data can be stored there, it's sleeping there. When we want to manipulate the data, we need to wheel it into the surgical room to do surgery on it. And that process is called loading data. What we have to do is that there are three elements to loading data. One is, where is the data? What's the room number? Where is the data? Second is, where to copy it to? Which of the 32 surgical rooms are we going to? Which register are we going to? And the third amount, which is not so comparable to the hospital example, is how many bytes do we want to copy? Because there could be a register in memory that has, I'm sorry, not a bit register. There could be, a register can hold up to 4 bytes, but it doesn't have to have all the data from that place. In other words, I could go to the room, and in the room there's 4 bytes. I could take just one of them and put the one into the register, and the rest of the register I'll fill with either zeros or ones. I'll fill, if it's depending on what I'm doing. If it's a positive number, then I would fill it with zeros. The negative number, then I might want to fill it with ones. So it will retain its negative properties. Remember, negative numbers always start with 1. And not only start with 1, they have to have, if you represent, let's say, a negative number in 32 bits, you got to have a whole lot of ones in front of it, even if the number is small. If the number really is just like, 1, 0, you'll have to put a whole lot of ones in front of it in order that, because as long as it's 1, 0 there, it'll, if the first 1 0, then it'll be a positive number. So you gotta do sort of like, you gotta backfill. You gotta fill it with it's called sign extension. You have to extend the sign. If the sign is 1, you have to extend it all the way through so that the whole register will have that sign. So my point was that you can take only 1 byte from memory and put it in the register, or you can take 2 bytes, or you can take 4 bytes. You can't take 3. It's either 1, 2, it has to be a multiple of power of 2. So either 1, 2, or 4, and then you put it into the register. So that's the amount, how many bytes I want to copy.
Isn't each number 32 bits? And
Yes, every register is 32 bits, but but data in the memory is every single byte has its own address. So I could theoretically grab any byte and say, put this small byte, a piece of 8 bits into the 32 bits of memory, into the 32 bits of register space, and then I have to fill in the rest with the appropriate number.
Would that be a chunk of a number though? Let's see when 32-bit number.
No, what about a character? You learned about characters in C++. Characters are 1 byte long.
Yeah.
That's it. You can, in 4 bytes of data would be 4 letters. If I want A, B, C, D, I can store it in 4 bytes.
So I can never manipulate an array more than 32 numbers in a register?
No, I need to know the location. Let's have an array and it's spread over hundreds and hundreds of bytes. If I know somehow the location of a particular byte, I can grab that byte and put it in a register. I can grab any byte of the array that I want. How exactly I know that location, we'll get to. So here, look at this example. Here's my new command in C++. My array at location A, add to it H and put it in G. Now, we're not going to talk about we're going to use the command load word, LW. Word means word length. What's word length in our chip? 4 bytes. So I'm saying I'm asking for 4 bytes. I'm not asking for 1 byte. Because I'm assuming that this array, that this C++, these variables were, let's say, integers, and then they're 4-byte integers. So I'm assuming that my translator, I don't have the whole line of code here, but I don't have the declarations. But let's assume that they're ints and they're 4 bytes. So this line will be correct, load word. Right? So I'll do load word, get me 4 bytes. Where to put them? Into T0. Where to get them from? So now I need the address of the array. So if register 3, for now, let's just say if register 3 magically already has that address in it. Essentially, it's a pointer. It has the location of there's a value here in S3, not the value that I want to copy, the location of the value I want to copy.
So it has an address.
It has an address. Somehow it got that address. We'll talk about how it gets that later. But for now, just imagine that it had the address. It's like address 4 million. So that 4 million is there. This 8 is that 8. It means offset 8. It means not the beginning of the array, but 8 spaces over. Grab that and store it in T0. Now, before you ask a question, just notice the following example is not fully correct. We'll see that I'm going to correct this. This is a little bit wrong. But now you can ask your question.
So there's no types in assembly. So
Very good point. There are no types in
So-
assembly.
if we add a string character with the number, it's just gonna add the bytes of whatever the ASCII code for that variant.
Yeah, exactly.
We're gonna get
From the
something-
perspective of assembly, it's just numbers. If you put the value A in an array, that's capital A is 65, so you'll get 65 in your register. And then if you print it, you have to tell it, do you print it as an integer or print it as a character? But yeah, everything is just numbers.
So I have a question. So two-parter, what does load word do exactly? It just loads something from memory into a register,
Yes,
and it can only load.
from this place, offset by this amount into this register.
And our 32-bit system, we can only, that register is 32 bits.
That register is 32 bits,
And
yes.
you can only load in a power of 4, so you can only load in 1 byte, 2 bytes, or 4 bytes.
Yes. But if I did load word, then I'm already telling it copy 4 bytes. If I wanted to copy only 1 byte, I would write LB,
Okay.
different command. And then it would just take the single byte that I'm pointing to. But when I write LW, it knows not just to take 1 byte, but to take a whole stretch of bytes, 4 long.
So if you do LBW twice and load in.
You can't do LBW, there's no such thing.
LBA,
You could do LB, you could do LB and you could copy the 4 bytes into 4 different registers if you wanted. But you couldn't copy the 4 bytes into different places in the register. This is going to copy it into the beginning of the register. And then, in other words, if it would be LB, then you would copy a single byte into part. I'll draw it on the board.
Is that why like programming language is either 1, 2, or like there's no variable in C that has 3 bytes in them? Like they're only 4, 8, or 2, something like that.
There's no what?
Like I'm saying in C++, for example, char is 1 byte and int is 4 bytes, so only like 1, 2, 4, like that.
Yeah, there's no 3 byte.
Is that because of assembly?
Yes,
Like,
yes. There's no 3 byte
yeah, that's what I'm
character type,
saying.
exactly. So 8. If I did something like this, so what would
So
happen?
it's doing the math to figure out where that address is.
It's gonna find a byte from memory, and then here's my register, T0. And it's gonna put over here the byte that I specified, and these other bytes will all be, well, let's say for the sake of argument, zeros.
But those blocks is still T.
So if I look at T0, I'll see a whole lot of zeros, and then I'll see the actual data I was interested in. Because I did load byte, but when I do load word, if I do load word, then it'll copy this, whatever's at that location, it'll copy it here, and then it'll copy here, and then it'll copy here, and then it'll copy, as it'll fill in the whole thing with 4 different bytes, starting from that location. As it'll, if I give it, let's say byte 0, it won't just copy byte 0, it'll copy byte 0, 1, 2, and 3. Because I did load word. If I did load byte, it would have just taken byte 0.
So top example, you do load byte in the bottom examples.
This is load byte, this is load word. There's also load LH. Load half. Half a word for 2.
Just review what we did last class, is this middle idea or big idea?
I have a slide about that. Oh, wait. So, okay, so
Enough.
guys, you understand this? That's equivalent to this part of the command. Because I couldn't just do the H plus this. I can't do surgery in the sleeping room. This is like saying, do the surgery on the array directly. And he says, no. First copy from the array into a register T0. Then you can do your add with the T0 and the S2, which is our H, into G, which is our S1. So I had to first load him up. Now when I loaded him, it's a little bit different from my mashal, because my mashal, in my example, the person moves and he's no longer in the sleeping room. Here, when we do load, we're not moving it and taking it out of memory. We're copying it. So it actually still exists in memory. It just also exists in the register. Yeah.
All the S, S are locations of memory.
Registers. Anything that starts with $1 is a register. We have 32 of them.
We're not pulling from memory.
No, because this S3 is in that memory, somebody in my program earlier, I already put the location of that array into S3. So S3 is set. He's got some kind of address. And I'm using this expects an address over here. And if the address is, let's say 4 million. So I'll go there and I'll see at address 4 million, I have the value 6. So I'm copying 6 into T0.
S3 is an address into memory.
Yes. S3 is just an address. That's what it says. S3 contains the memory location of the array. Okay. But this example was wrong because every byte has its own address. Like I said, right? Every single byte has a different address. So I can't. So if I want to translate 8, which means 8, then 8 integers forward, I really have to do 8 times 4 because every integer is 4 bytes. So I have to write 32 here. Because 4 times 8 is 32. In other words, this is saying, in this C++ code, he's saying, go ahead 8 bytes. And not 8 bytes, go ahead 8 of my type, whatever type this was. This was, let's say, type integer. So go ahead 4 bytes times 8. But when I'm doing this load word, he doesn't know anything about integers. He doesn't know that this is pointing to an integer. He just knows it's an address. So if I want to go 8, offset 8 from there, forward 8, then I have to actually go forward 8 times 4 because I really want the 8th integer, not the 8th byte. And integers are 4 bytes long. So I have to go further. So that's what this 32 is. I have to calculate that. Now there's the machine doesn't know where I want to go. So that's the correct version of that example. Everyone understand the difference?
It's still adding the addresses.
The exact same thing. I just changed the 32.
Saying that-
Here, if you notice, I wrote an 8.
Mhm.
Everyone understand that's wrong?
Yeah,
And here I wrote a 32. Everyone understands that's right. That's the only thing I'm trying to show.
What's the point of this offset thing? Why don't you just put in the address of that place in the array?
Because well, for example, well, you could ask the same thing here. Why did he write 8 over here? Why didn't he just write my address plus 8?
Or like the pointer notation.
Yeah, in other words, this is saying, I have the address, but I want to go 8 away from it. So I'm translating it directly. If this is acceptable to you, then this should be acceptable to you.
It's also what
It's
helps
the
us
same
with
thing.
rate.
It's just, yes, okay. Now, I did record the class, so hopefully it worked. I am recording. Here, I want to show you this picture. It's a little,
Well, you just show us with the address that goes into the machine code or the some,
this command,
the machine code has the actual address or it says this address plus study thing in the machine code.
no, in the machine code, it'll write, in the machine code, we'll talk about it, but the machine code for this line will have S3 in it. It won't have the address. We'll get to the, I don't want to jump ahead. I have slides that'll go through everything, okay?
Yeah, on the slide.
No, well, it might, it depends how fast we go. Of this lecture, not the scope of this slide, exactly. So here we have a diagram of memory. It's a very important diagram to memorize, kind of. At least generally memorize. You don't memorize the details, but the general idea is that at location, first of all, what does the 0x mean? Anyone know? It means that this number is in hexadecimal. If you, the 0x is just an indicator, it's not part of the number. It's just telling me that this number is in hexadecimal. And it's telling me that the value is 400,000. But it's not 400,000 decimal. Is it more or less than 400,000 decimal? More, because it's in base 16. So it's a lot more. But I'll call it 400,000 hex. So that is the location in memory where your program code is sitting. When you write a program, you store it, let's say, on the disk. You want to run it. The first thing you got to do is load it into memory. You can't run a program from the disk directly. You have to put it in memory. So it's where in memory. So we have set aside a place for it at 400. Why not at 0? Excuse me, because the operating system is at 0. That's where because the operating system is also a program and it has to be there all the time. So it occupies the first location in memory.
Like firmware.
Not firmware, operating system. No. It's a program. Operating system is a program like any other program. It's just sitting in memory and it's here in the memory. This is the program code. And then what's written over here is that this is text. We call it text segment. In MIPS, we're gonna in your lab, you'll call it the text segment. There's also something called the data segment, which is where your arrays will be. So when you do, see, as a static and dynamic is for like new type things. We're mostly going to focus on static. Regular array, static means that it's not created as the program is running, but you initialize at the beginning.
No, that,
Get outta here with
that's,
Static, guys, let's pay attention. Static means that the array is like, I create an array, int a parentheses 100. So now I created 100 integers and the name of the array is a. Where will that be? It'll be in the static data, not in the program code. The program code is where the actual program is. So that's the static data starts at 10 million hex. And the rest of it, we don't have to explain right now. But there's something called a stack and there's a heap, but the heap, we're not gonna talk about the heap. So mostly talk about the stack. The stack is for function called data. We'll talk about that when we do, well, you'll talk about that in the lab. Avi should talk to you about that when you do in one of the later labs. Not
There's no slides about that. Well, he'll have it on the slide, I guess.
he'll teach you, don't worry.
Can I ask, I don't know if, I guess you can continue go. I was curious, like the relationship between this and like, are you preparing us for a lab that we're gonna have to write in class there? Or is this just like general knowledge and he's also general knowledge and that's the class?
No. In general, in the lab, you'll be doing programming in MIPS. In this class, we'll be learning theoretical stuff about how computers are built. But this lecture in particular, I'm introducing you to the language also.
Okay,
Thank you for that.
thank you.
Okay.
cool.
So the static data is where we keep the arrays. So it stands to reason that if I make an array, what will be the address of it?
1 million?
It'll be 10 million.
10
And then if I make an array, another array, if the first array was 100 bytes, then where will it be?
400.
It'll be at 10 million plus 100.
Wait, 100, I thought each one, oh, because each
Oh,
byte,
400, fine, 400, 100 bytes, I said though. So
yeah,
if I make an array that takes 100 bytes, then the next one will be at 10 million plus 100. In other words, they're one after the other.
and I
the
call
arrays.
it by writing.
And I'll keep
100.
filling this up, and I'll keep filling this up until I, don't have any more space. Theoretically, I can put them all up there.
It's always at these addresses.
Yes, 10 million. It's actually, I think on the MIPS simulator, for some unknown reason, it's at 10 million, 10,000. They just, this is the way it's supposed to be,
Oh, they
but
took 10,000 violence.
in your thing, it starts a little bit off, but it's the same idea.
Well, you have very limited space for program code.
No, you have very big space. You have
Then you
You have
got
10
millions.
million minus 400,000, so that's 10 million almost.
But
10 million hex byte. That's enough.
like 10 what, 10 million?
Yeah, more, well, it's hex, that's more. Anyway,
Oh, 10 million.
data loading, oh, so I did this already. Now, look, here we're talking about big endian, little endian. if you want to say.
You like
So-
to mention like that.
I'll just explain it in a certain way. When I said over here, load word. This was the address of a single byte, true? So if the byte in memory was sitting here, let's say this was location, 10 million. In hex. Okay, so what do I want to get? I want to get 10 million. I also want to get 10 million in 1, 10 million in 2, and 10 million in 3. So the point is I specified 10 million, and he has to know that well, I can say it like this. There's different ways of saying it. I'll say it like this. He has to know that 10 million, should it go here or here? You see what I mean? Should the 10 million, should it be 10 million is over here? And then 10 million and 1 is here, and 10 million and 2 is here, and 10 million and 3 is here? Or should it be the other way around? Should 10 million be over here and 10 million 1? Which way do I start? Which way am I going? Which way are the other ones?
It's on the right, 'cause
Meaning memory.
Yeah. Which way are the other ones going?
Well, the computer is built to work one way or the other. That's the point. Some computers are old, they have to be consistent, you're saying. I got to do it the same. My register has to store it.
If it's already chosen.
Exactly. You're right. No, I'm just saying, yes, you're 100% right. I'm not going to choose
unless you're designing a chip.
unless I'm designing a computer. The designer of the computer will decide and set down the law that this machine is big endian or this machine is little endian. And therefore, a Macintosh, for example, is big endian. MIPS is big endian, but Intel is little endian. They're different in their assumptions about where data is stored.
What the game is called big Indian?
Oh my God.
Okay.
Oh, you're young, bro. This should have been standardized. It's crazy.
I
You
agree.
remember the
Your
whole thing
example
about
here is
big
big
endian,
endian?
little endian, right?
If it's starting in the.
Which one is which? Big Indian goes
No,
left to
it's
right,
not
right
even
to left?
objective advantage either way.
There is an advantage to them, but
Who is it? Oh.
Ring.
You get his number. What the fuck? That's his ring.
okay. It's really not that important. I mean, it's an important concept to be aware of. We're not, I mean, I'm not going to test you on that really.
That's all you need.
But I'm not going to test you on this big Indian little end, but it's an important concept, and it would be remiss of me not to discuss it in a course on architecture, because it is a real topic. But I'm not. It's not emphasized in the book really, and I'm not really going to emphasize it. I mean, there's another way of explaining it, and there's another way of explaining it, which is to say, when I specify an address, is he supposed to go up or down from there? Maybe that's a simpler way of thinking about it. I specify address, let's say I specify address 10 million and 4. Does he mean, am I supposed to take 10 million and 4, 5, 6, and 7? Or am I supposed to take 10 million and 4 and 10 million and 3 and 10 million and 2 and 10 million and 1? Which way am I supposed to be going?
It's like, yeah, which way are you accessing the information?
Which way am I accessing the information? So big endian means I'm taking the most significant bit first. I'm taking the most significant or byte, the MSB first, and then I'm taking. There are architectural reasons which I once learned, but I do not remember why big endian is actually better in general.
What does
So
the
the big
first
is-
line mean? The address of the word also refers to the leftmost byte of the word. What does that mean? Like the address is actually.
Well, MIPS is the big end, the leftmost byte. In other words, if this is my word,
Yeah.
it's actually referring to the leftmost byte, not the rightmost byte. So that's big end. That's the big side. This is the big end. This is the big end. This is the most significant bit or byte.
Yeah, it's like.
If I have a check,
MSB.
if I have a check for $1,000, would I, if I'm gonna add a 9, where would I rather put it? On this side or this side? I'd rather put it over here. Then I get more money. So that's the most significant. The numbers on the left are more significant. Numbers on the right are less significant. Pretty insignificant if I added it over here, just as we 9. Well, no, we'll move over everything. But the point is, most significant is here. LSB is over here. Least significant byte or bit. So big endian, I specify this byte. Little endian, I specify this byte.
Okay. But what does it mean that the address of the word also like the address of the word is one of
The address of the word, as we thought about it in the previous slide, which is really just an address of a byte in the word,
Okay.
is referring to really just the leftmost byte of the word.
It's like saying you have an array that stores a bunch of
Although
addresses, and the
English-
first one marks an address, right? How do I access it through the first one? We're just
But-
saying,
but
do I
that's
read the
the
first
address-
one from the
that
left to the right or right to the left?
Basically English or Hebrew.
Okay, so let's go on. Storing a word in memory. We learned about load word. Let's talk about store word. It's the inverse. And basically, here's an example of C++ where I say, take this address and then store it in this address. Take it from 8, add H to it, and store it in 12. So how would I do that in MIPS? I would do the same thing I did before. Load word 32, the 8 becomes 32. S3 is the address. Put it in T0. Now I got it in T0. Add T0 to T2 and put it in. Well, I can put it in T1 or I can put it back in T0. I don't need T0 anymore, so I can overwrite it. So I'll store it in T0. Now I need to go back into the sleeping chambers, right? Into the store, into the memory. So I'm going to take the value that I have and put it in this way. Store word means
Store
go.
word works the opposite way.
Yes, it's a little bit confusing. Store word, I put this over here and the arrow says, take the register and store it in this location. This says, take this location, so extract from it the word that I want and put it in this register. So the arrow points to the left. Here, the arrow points to the right.
But it means if you're taking something out and putting it back, you can copy the line.
Take it out, put
If
it
you're
back.
taking a
copy
piece
the
of
line.
data out.
No, but I
putting
changed
in.
it.
I'm saying after you changed it, you can put it back in with the same command almost.
But I have to call it store word, not load
Say you
word.
just change the letters and then it's the same thing.
Yeah, yes, I just changed the letters. It looks the same.
Right.
Exactly. Yes. What?
Target of store word is.
The target is different, right? Exactly. Here, the target is here. Here, the target is here.
Got it.
Okay, let's go on. Now there's another command called add I, which is different from add. If you notice that add I, I stands for immediate value, which means that the value is immediately in the command. In other words, this is not a register. This is the value that I want. I don't give it a register, I give it a value. The value 4 should be added to S3, and then the target should be also S3. That's what I said here. Take whatever I is, add 4 to it, and put it in. So this is a different type of command than what we've seen because it has only 2 registers. It's different from add. Add takes 3 registers. This takes 2 registers. We actually say this is a different type of command. We have 3 types of command, which I like to remember as Rabbi Isaac Jacob, because R, I, and J are the 3 types.
That's my grandfather.
Isaac Jacob.
Yeah.
So Rabbi Isaac Jacob. So this is what's called an I type. Can anybody guess why it's called an I type? Because it's for immediate. Immediate, that's the I over here. Now, a little bit tricky thing, if you think about it, I'll tell you like this, the I type has two registers. It's the only command that has two registers. Because the register type, the R type, it stands for register, that's the regular add that we saw, which takes 3 registers. The R type has the most registers, that's why it's called the register type. What is the load word type, if you could choose one of those two? If you think about it, it's actually a load, it's actually an I type, because it has 2 registers. Notice the similarity between add I. It has 2 registers and an immediate value. There's an F32 is an immediate value. So it's actually an I type.
What are the 4 types?
R, I, and J. We'll learn about J later. J is the easiest
What's
one.
R?
R is like add. Add is R because it's the register type. It has the most registers in it. Look how many registers. 3. That's the most you're gonna get.
What do R, and J stand for?
I immediate, R register, J jump. We didn't get the jump yet. Okay.
Wait, what does the second parameter in ADDI do? Why is it?
So the second parameter is like this. Look, this is a translation of this. I take my I and I add 4 to it, and then I store it in I. If I take my S3, I add 4 to it and store it in S3.
Does immediately mean like
This is the target. These are the 2 parameters that I'm adding together. In this example, I used the same register twice. I could have had 2 different registers. All right, now let's talk about this part of the course, which is interesting. Now we're getting to exactly this issue, which is how do I store or how do I represent a command in binary? We're going to learn how, guys, pay attention, please. Turn, face forward, pay attention. This is important stuff here. All instructions such as we have learned up to now must fit into a 32-bit machine language instruction. We said already that they have to be 32 bits. So if I had a command like this, add T0, S1, S2, let's translate it into its components in machine language. So in order to understand this, actually, the best thing I can do is show you the, probably Avi showed you this too, the Mars compiler, Mars, what's it called?
show me the MIPS.
The Mars.
Oh, Mars? I thought it's the MIPS.
No, Mars. Mars is the name of the assembly. No, the MIPS
What's
is
AR
the
stand for?
machine. Mars is the program.
And that stands for.
I don't remember, but it stands for something. Okay, look here. This, what the important thing is this table over here. Hard for you to see it, but what it says here is register and then name, number, and value. The values are almost all zeros. Some of them are not, but almost all of them are zeros. X0 is just that's hex, and then and then zeros. And now over here, we have the name of the register. For example, T0 over here, his number is 8. It's just there on a table. Register T0 is 8. Register T1 comes right after is 9. T2 is 10. T3, 11. T7, 15. Interestingly enough, T8 is 24.
Yep.
They just skipped over there. I don't know why, but that's where it is. So up to T7 is there. After you get to T7, you get A. At 16 is A0, A1, A2, A3, and then oh, so that's not A. Is that A?
I can't see.
You can't see and I can't see. No, here's A. Sorry, here's A. A0 is 4, A1 is 5, A2. This is S. At 16 is S0, S1, S2. So you see that every register has a name and a corresponding number. The machine actually understands the number, but we like letters. So if I go to S1, guess what its number on that table we just saw? It's 17. Remember, it was 16 was S0. And so S2 is 18. Now, we're not talking about the value. Get this point clear. It's not the value in the register. It's the name of the register. The name of S2, its name, its ID number is 18. T0 is 8. The 0 over here is called the opcode, which is operation code, tells me what operation I'm doing. 0 is for add, but actually 0 is not for add. All R type instructions have an opcode of 0. how do we then differentiate between them? We use the last section over here, which is called the function area. And that's going to tell us that it's add or subtract or some other R type. So 32 is telling us that it's an add. The 0 over here just tells us it's an R type.
It's an R type.
Why? It's an R type. If it's a 0 over there, it's an R type. This number will actually indicate which command in particular it is.
What's
What's the shot? Why? When do I? Well, for an I type, this will not be 0. For the I type, this will tell me what command it is, and I'm done.
So Addy would be a different.
We'll see. There's a certain beauty in it, but
Okay.
there's a certain reason for it, which we'll hopefully get to. The 0 here, it will not be a 0 if it's an I type. It'll be an actual number like 4 for add I, and for a store word, it'll be 23 or something. Now, there's an actual number here that will tell us what operation it is, if it's an I type. But if it's an R type, it will just be a 0, and I'll have to look at the end to find it.
So there's no end if it's an I.
If it's an I type, there's no, this section is used for something else. We'll see what it is.
What number is subtract?
What?
What's the name of subtract? It'll be a 0, and what number will be in the end?
Oh, I think like 34. I don't remember. Okay. Also notice that there's a little switcheroo going on here. This S2, S3, and T1 is T0 is over here. The target is on the left,
Yeah.
but over here, the target is on the right. That is a change that was made, let's say, by Grace Hopper. In other words, she said, for writing it, it's easier to think about the target on the left. But the machine, it's easier for it to have the target on the right.
What's the unused?
So there's a switcheroo going on here. Be aware of that.
What's the unused?
Unused means that part of
Oh, it gives
the,
it like a space before the command.
yeah.
Oh, cool.
Now, I have okay,
What is-
I have a question. How many bits is this area gonna be? No, this whole thing is 32. This from here to beginning to end is a command, it's 32 bits. How many bits will just this area for the S1 be? Well, it has to be big enough to store any possible register number. What is the range of register numbers?
32.
From 0 to 31. What's the largest value? 31. How would I represent 31 in bits?
All ones.
How many ones?
8.
5. 4 ones is 16, is 15. And 5 is 31. So this is actually 5 bits, and that's what we'll see in the next slide.
What was the switcheroo? I just didn't get that.
The switcheroo is that this is T0 is on the left, but T0 is on the right.
In the actual.
In the actual encoding, this is called the encoding
Uh,
of the command. It actually moves its location. That's just the way it is. That's just the way it is.
So then that should be 30.
So let's look, wait a second, let's look.
what is this encoding? Is that the actual encoding of how the command itself, or when we write the command?
That's how the machine will get it.
That's
You'll
how the machine
write
will
it
get the
as
command.
add like this, but the machine wants ones and zeros. The assembler will have to encode it.
Gotcha. So why wouldn't we write it the way they encode it? Like, why wouldn't we just write it?
Oh,
Like,
they switched the, why they switch the order?
Because some things are more intuitive. you said.
Yeah,
For-
because
for us, it's
you
like
know, normal
X equals-
programmer doesn't have to do the encoding, the assembler will do that.
Hmm.
So as long as I'm free to do it any way I want, he doesn't have to know this.
okay.
So for him, it's easier to put on the left.
That makes
Okay, so let's look at this. This is the same thing. Instead of calling this the T0, because that was just an example, T0 and S0. That was an example. We actually have names for these areas. There's actual names. OP stands for what? Opcode. RS stands for what? It says it, yeah, registered storage. Oh, you guys are so smart. RT, RD. This is that area that I said was unused. It means shift amount and function. So look, this is RD. Why is it RD? Because it's the destination, it's the target. The RT it's a little bit confusing because these are both called register sources, but this is RS and RT. Why is this RT? Sometimes this is the target. No, because sometimes T can actually stand for register target. Sometimes this field is a target on certain commands. When the RD doesn't exist. Sometimes the RD doesn't exist, and then the RT becomes the target. So RD is when it's there, that's the target, but when it's not there, then the RT is the target. So this is the structure, and notice it's 5 bits because this is a register. Takes 5 bits to identify a register. 5 bits, 5 bits. That's 15. This area, let's say, we're not going to talk about right now, but that's the other 5 bits. That gives us 20. 6 for the opcode and 6 for the function code. That gives us 32.
Are we gonna have to be able to translate?
Yes.
Into just like more
Yes.
zeros?
You have to translate from ones to zeros from, but you'll have a cheat sheet. You'll have something called the MIPS green card, which has in it what the you're not going to memorize the opcode. It'll tell you, it'll actually give you all the information. It'll tell you the format of the R type, J type, and the I type. It'll tell you what the opcode for everything is. And it'll even tell you that there's a switcheroo going on if you look at it carefully. But you'll still have to, so you have to use that as a sort of map to then decode. It's really not, if you understand what you're doing, it's not hard.
That's what.
No. There are some things that are hard. Do differential calculus is hard.
No, that's all right.
Oh, no way. All these together are 32. Oh, that's.
So now we have the I type. The I type is interesting because the I type is saying like this. We want remember we have an immediate value there, like add 4 to our I or to our register. But what's the largest value I can put there? I'd like that value to be as large as possible, right?
Yeah.
I don't want to be limited. Are you guys with me? I feel like some people are talking and doing other things.
Extremely rude.
Wait,
It's not only rude, it's bad for your own education.
before we explain this, there's different types of the encoding for each of these things. Like the
Yeah.
archetype is what we just saw is the archetype.
Yes, now we're learning the encoding for the I type. And I'm giving you a preparatory remark, and I'm saying that we would like to have the largest possible number in our storage because we don't want to be limited. We'd like to have a very big number there. So, but we have certain limitations because an I type has 2 registers and an opcode. So 2 registers and an opcode already takes up 16.
Wait, it's 2 registers? I thought each command was one, but.
No, remember the I type. Let's look at the I type.
Well, I thought isn't a command a word as well?
Here's an I type example. This is a command of I type.
Yeah.
This whole command has to fit into 32 bits.
Which, yeah, every command is a word.
Yes,
Right? It doesn't matter what type, it's always a word.
yes.
Okay, so, and registers are also.
No, register, remember, it takes 5 bits to refer to a register. A register is itself 32 bits, but there are only 32 of them. So I can refer to them with 5 bits. If there were 64 of them, how many bits would I need?
I mean, you need twice as much.
Which is what, how many bits would I need? If it's 64 bit, if I had sorry, not 64 bits. If I had 64 registers and not 32 registers, how many bits would I need to refer to them all? 6. Because 2 to the 6 is 60 is 64. It's like if I had 64 people in this room and I wanted to give each one its own ID number, I'd have to have how many binary digits? 6 binary digits. And then I could reference the first one is 0 and the last one is 63. But in this case, I only have 32 registers. So you see, actually, that's another reason why we limited the number of registers. Because if we had more registers, if we had 30, instead of 32, if we had 33 registers, we'd have to waste a whole nother byte, a whole other bit, sorry, a whole other bit. This would have to be 6, and this would have to be 6. And this would have to be 6. Because each of these has to be for a register. The minute I go beyond 32, I need another bit here. And if I went beyond 64, I need 2 more bits here.
But you have 64 bits, it's awesome.
No, let's say I had 32 bit. Let's say I had a 32 bit command, but I had 33 registers.
Oh.
If you look over here, actually, look at this. I actually have more registers. Notice the numbers stop at 31 and there's 3 more registers. I have extra registers, I can't access them. And because if I would be able to access them, then I'd need an extra bit and it would throw off all my things. But I needed those extra registers. So I just made them and I can't access them. They're there for other purposes, but I'm not going to access them. If I wanted to access them, I need an extra bit and it would throw off the size. We need to fit everything into this size. So we're limited. So look at this. In the I type, I have 5 bits again for each register, 6 bits for the opcode. that leaves me a grand total of 16 bits for the constant value that I want to put, or the offset, or the, remember, it could be a load word, which gets to the offset. So in other words, I can only put a value here of 2 to the 15th. Plus or minus, if I want positive and negative values. So 2 to the 15th or 32,000. In other words, I can't do, for example, add I with a number larger than 32,768.
Having 32-bit integers, yes.
You understand what I'm saying? If I want to add, let's say, 100,000 to a number, I'm gonna have to do it another in several steps. I'm gonna have to do it in more than one step. Add I is limited. But notice that I maximize this value here. Now all of a sudden unused space. Remember, it's in the R type, it was unused, but now it's used. Now I'm using it. I got rid of the RD. There's no RD here. This is the and the opcode now will tell me what command it is.
I don't know if it's a constant or an address.
Depending on what command it is.
Okay.
If this command is a load word, then this will be an offset in the array or a store word. But if it's an add I, then it's a constant. And there's another one that it could be just an address. Okay, so now let's take an example like this. I have a command. Let's go all the way through. I have C++ array 300 plus H array 300. So I'm taking the value, adding H to it, and putting it back in the same place. 3 commands in assembly. Load word, why is it 12? Why is it 1,200? Multiply by 4. T1 is assumed to be my array. And T0, by the way, is number 8. T1 is number 9. So T0 is where I'm storing it. Then I stored it there temporarily. Now I add to it S2, and then I put it back with store word into the same location. Now let's translate that into.
What is the hash T0 equals 8?
Is that a comment?
That's a comment. Yeah, hashes. These
That's
hashes
saying-
is the way you comment in this language.
So
Oh,
Instead of a double slash, we use the pound sign or whatever you want to call that. And that's as a comment to myself to know that S2 is 18, so that I'll understand why there's an 18 over here.
Yeah, that's your H here. You're pretty much like adding it to the location and then putting it back in the location. Like
Right,
you're pulling from
exactly.
the location, adding 18 to it and putting it back.
Exactly. No, the S2 is the H, yeah.
Yeah.
So look, the opcode, the RS, the RT, the RD, the address function. So look at the first command. The first command is actually an I type. So here's the opcode for load word 35. I know that from the MIPS green card, which you'll have access to. You can Google it.
35 is what? Load
Is the opcode for load word. RS is,
Why do we care about the opcode?
because otherwise how's the computer know what command you're doing?
So this is just on the computer. It's not relevant as a programmer.
No, it's on the green code. It's like,
When
how,
we're writing.
how do I know what code to give?
Saying when we break, we have to use that knowledge that opcode.
This- I am not teaching you about the.
Yeah, I'm just asking, so
This is information for the lecture, not for the lab. in the
I'm
lab-
just asking if that has any practical.
It has nothing practical to do in the lab, but for the exam, you have to know it.
Yeah, I was just asking.
So 35 is the opcode for load word. Now, notice that I have 9 over here and 8 over here, right? T1 is 9, T0 is 8, and the order switches. Why is that? Well, that's just this. That's our switcheroo. 9 is here, 8 is here, and then this is blank. Really, what I meant to write is 1,200 in this whole space. This whole space has the value 1,200. Now I do,
Which one's the 8?
the 8 is the T0. That's T0, that's T1. So I switched the order. So in other words, this value is going to be combined with this value to get the actual location that I'm interested in loading. And that'll be stored in here. And that's, if you think about it, it actually makes sense here because this is the RT, this is the destination. The only problem is that here it doesn't make sense because this is store word. And again, I put the T, it stays in the RT. This is the RT. And this is the RS. And I store it in the same location, 1200. And 43 is the opcode for store word. And in the middle, what I skipped is add. And notice that since it's an R type, there's a 0 here for the opcode. And there's a 32 over here in the function. And then I have my 18 is, remember the order, remember the T0 goes to the end. So this T0 is over here, this T0 is over here, and this S2 is here.
It would be so bad if we just put the 32 on the left.
This is the way it is. It's just accepted. Now,
Just accept it.
no, I'm saying nothing to do about it. You could design your own computer differently.
Just make the new one.
Now, if I take, wait a second, if I take these numbers, like, for example, here, let's do like that. If I take this number, for example, 9, this is 9 in hex, in binary. If I take 35, this is 35. 8, 8. Notice 8, 8, 8, 8, 8, 8. Here is the representation of 1,200. And again, 1,200. Here is the unused section. Here is the RD 8. And here is this is 32. That's how you represent 32. So actually now I have a string of ones and zeros. And that's what the guys in the Navy were doing when Grace Hopper came along and said, you guys are writing this? And they said, yeah, why not?
What do they write?
Imagine like a bunch of big
Now they
stuff.
write. So I'm saying that's the final thing the machine wants.
That's how they play.
This is what the machine can understand. That's what he likes. This is what you guys like in C++. This is what you're going to do in the lab.
So it's something none of us.
What is the, can I ask what the, you scroll down, sorry, can you go to the next slide? What is the second to last row on the right? What is the
This?
18 there, yeah.
Well, this you mean?
Yeah.
Well, this is just, you have to view this whole thing as one long box, and that's 1,200. Because remember, it's 1,200.
Yeah. Oh, those two numbers combined is 1,200.
Yes.
Oh,
Those three numbers, the zeros here don't really affect
great.
it,
One,
but
okay.
this is all one
Got it,
space.
got it, got it.
Remember, it's 16 bits.
One,
for the-
thank you.
So, so all extra zero, we add them at the right.
Do we have a break during this period or no? Not that we need.
Not that we need it.
You want a break?
Yeah.
You can have a break.
I don't know about one. It's like-
Well, I think it's built in a 5-minute break. There is built into the schedule a 5-minute break. We can have a 5-minute break. Then I have to stop the recording. And I have to figure out how to do that.
They're really not taking off a lot of, like, my code would not run, they're like. You're good. Correct idea.
So now, the mystery that we were all talking about was how to get the address actually of the array. So we're still not getting everything because we still don't know how to create an array.
10 million number, right?
It's the 10 million number. So what I could do, as long as you mention 10 million, I could say like this. I could just say, this is actually pseudocode. LI is pseudocode. You're allowed in the lab to use this command. There's two pseudocodes you're allowed to use. One is LI and the other is LA. But what I can do is like this. I can say, take this number 10 million in this, I said theoretically, it should be 10 million, but in the Mars simulator, it writes it as 10 million, 10,000. So I just take that value in hex and do a load immediate, which means copy this value into the register T0. And now I got the address of my array, assuming my array is at the beginning. That would be one way of doing it. The other way of doing it, which is a little bit more human-like, and that is to say LA load address of my array, assuming I declared my array. We'll see how to declare an array. But assuming I declared the array somewhere in the data, then I take the name of the array and I just say, grab the address of that and put it into T0. And I let the simulator figure out how to get the actual address. It'll be the same thing. It's just, I'll get the same result.
Wait, one puts it in and one gets the address. Like
Either way, T0 will get the value,
we'll get the,
same value. 10,
so that's
10.
setting the address of T0 to
Just
be.
saying load address. This is special command
Load address to what though?
to the register that I have.
the register,
Load to
okay.
this is the target, to this location, the address of this array. Special command LA just for that purpose. Sometimes people use it for other things and it's wrong. The compiler will let you get away with it, but I won't, but the lab teacher won't. My address, put it into T0.
So LA is load address.
LA means load address of what? Of this array, where to? T0. It's the same as this command. It's actually the result at the end of the day, T0 will have the same value.
But how do I get an array?
How do I declare an array? We'll see. We haven't yet seen.
But what would that be? What would my array actually look like? It would look like a dot, like a.
We didn't see it yet. I didn't show you. I think I have a slide and then you'll see.
Okay.
Oh, here's the next slide and there you see. So it's like this. Here's my LA and the name of my array is list. Okay, this is actually, I'm going to show you this, but then I'm going to skip this rest of the slide. This I'm saying the data, the dot data means I'm in the data segment, means copy this code. Remember I showed you that diagram of the data and the code section of the memory. The memory has all that space and the section is for the data. Data is where I put the arrays. So I actually write the word data here, dot data. I write dot data and then I write list colon and the name of my array will be list. And then I write dot word to indicate that each of these numbers is intended to take up an entire word. If I write dot byte here, then they would each take up a single byte. But I want them to take up a word, so I write dot word and then I write my numbers. And then I can do dot text. Text is the text section or the code section. There now I can actually, if I forget to write this text, then it'll think I have no program here because it'll think this is some kind of weird array or something. It won't understand it. I have to write text here and then I write.
What does the text do?
Text says now I'm beginning to write my code.
This is how we put it into Mars.
This would be a program in Mars. So now these are comments over here, and then this is a comment. And I do LA, load the word, load address of list, which is going to be, of course, 10,010,000 because I didn't put a number array before it. If there would be list 1, list 2, list 3, each one would be exactly adjacent to the next. When the one ends, the next one will begin. With no blank spaces left in between, one after the other. So but I write list here, I do LA list into T3. Now T3 has the address of it, of the array, and I can refer to the 24th location of T3 and put it into T5 with load word. Here's my question for you to review what we've learned. What is the value that T5 will have now? What's the exact value in decimal?
In decimal?
In base 10.
Oh, we got this. We can do this. 1.
Yeah, I went to -2.
I like having different answers. That means it's a good question.
Oh no, -2. Yes, right. I was doing divide by 8. Yeah. Really.
You're differently stupid. Okay, what's the answer? Well, what do I gotta do with 24? What's the first thing I gotta do with 24? Divide by 4, what do I get? I gotta go to the 6th location of the array. What's the 6th location? Now you gotta count. First of all, just remember, this is 0. 1, 2, 3, 4, 5, 6. A lot easier for me because I can point. So it's 4. The value would be 4.
I got intimidated by it.
Okay. That's it for this set of slides. The rest of the slide, you're welcome to look at. Oh, actually, no, it's not it. I should explain. Sorry, I should explain the J type instruction. The J instruction is the simplest one. Look at it. It's just the opcode and the target. The target means where I want to jump to, because I can write code. Wait,
Get enough with your
What's a
go-to.
go-to?
Except in assembly. Then use it.
here,
all.
look at this code here at the top of your screen. I'm sort of jumping ahead, but I can do jump exit. That means jump to a label called exit. Here's exit. So I'm going to skip over this line here. Yeah, I'm skipping over that line.
Yeah, that's very
And I'm jumping to the exit. So this command needs to know where that exit is. It needs a address of that exit. The truth is this is allowed to do with just a label, but the encoding of this will be different. If this is line, let's say
400,020. Then this will be line 400,024.
Oh.
And this will be line 400,028. So this jump will actually be jumped to 400,028. And it'll get us to that line. So that's what I mean when I say over here that the target is a 26-bit address. Means I'll jump to a 26-bit location.
In assembly, you can use labels.
Yes.
So there's one opcode that's like a jump command, and then it'll use the rest of the 26 bits to know where to jump to and what to do.
Yes.
Okay, it's not just like there's also actions in there, or it's just like you get the opcode and the 26
Well,
bits,
there's
then
two-
where to go.
You can see there. So it just jumps there and then starts executing
Okay.
from that location.
So that those labels, you can put them anywhere in the code,
Yeah.
so you can really just have like code.
With lots of labels, you don't even have to use them. You could have labels with colons after them and then not even go to that place. Just stick it there just for your own reference. Just to label, mark this section of the code with the name, for example. What?
Would this be used for loops?
This would be used for loops. So here, first of all, before we get to loops, I want to talk about this command. It's a command called branch equal and branch not equal. Branch is another kind of jump. Because what it's saying is jump, it's an I type. It's an I type, it's not a J type, but it functions as a jump. It jumps you, it moves you from one line of code to a different line of code. It's basically the same idea as your if. If you think about your if, you say, if this is true, then do this. But if it's not true, then jump somewhere else, right? Then skip some lines and go somewhere else. So we use the branch when we're doing the if, but we really only have two things, if equal and not equal. We don't have if greater than or less than. There's a way to get around that problem, but we don't need the greater than less than. We're just gonna do equal, not equal. Technically, we probably could get away with just having equal and not even have not equal. But because you can compare it to something else. So these are I types. So let's look at an example in C++. This is actually, I guess, 2 lines of code, but or whatever, however you want to think about it. If I equals J, then do F equals J plus H. But if it's not equal to J, then do F equals J minus H. So this is a quotation from the book that I didn't want to have to prove to you, so I just quoted it. In general, the code will be more efficient if we test for the opposite condition to branch over the code that performs the subsequent then part of the if. So in other words, what I'm going to do is branch not equal. Instead of saying equal, I'm going to say, is it not equal? If they're not equal, if I and J are not equal, then jump to the else. You see what I'm doing? Then jump to the else section.
Where is the, oh, it's right. It's not,
And here's the else.
you
I
right.
made a label,
Oh,
branch
the third
not
row.
NE not equal. If they're not equal, then jump to else, which is over here. And then I'll do the else, and then I'll get to this exit and I'll be done. The exit won't do anything. It's just like an empty line here. So I'll be done. And here I do the subtraction. So I do the else. But if they are equal, then I'll automatically just go to the next line, and then I'll do my add, which is what I wanted to do if they're equal. If they're equal, add. So here's my add. And now I have to have this one tricky line here. I have to say jump exit, because if I don't write this jump exit, then he'll also do the subtract. He'll just go to the next line. I got to make sure to skip this line. So I need to throw in this jump.
But it's an else.
Doesn't matter. These labels are not really code. In other words, they're just for me as a human being. It's not going to see that there's a word else. This doesn't have to be else. This could have been hippopotamus, and then I would write hippopotamus here and hippopotamus here. It's like a break. There's no meaning to the word else, is what I'm saying. It's just that I just chose that name for you to understand it. But when it runs here, there's no reason why it won't run this line. Just because of the word else in front of it doesn't tell it not to run that line. The only way to tell it not to run a line is by putting a comment in front of it, but then it'll never run the line.
So if you have 2 if statements, you have to use different labels, or can you use the same, they're not nested.
If they're one after the other, I could use, oh no, I can't have, no, in the whole program, I can't have the label twice. In other words, the label can only exist in one location, because otherwise, when I say jump to that location, he has to know where to go. You can't have 2 of the same name.
What's the convention?
So if I have many if else's, I can't keep using else and else and else.
You just use else
I'll
one,
use-
else two, else three.
Yeah, but you know what the better names are gonna be?
The
Are
actual
gonna be,
function
yeah,
itself,
what you're
like
doing
what
there,
you're
exactly,
yeah.
what you're doing there. If, in this case, very simple, but I might call the label subtraction. And the label, and here I might call it exit, which is what it's doing. So else is maybe a bad name, it's maybe better to call it like what I'm doing at that line.
What about like else subtraction?
You could,
What here is a label, the word else and exit is also a label?
yes,
Okay.
anything that's followed by a colon is a label. Actually, you've seen that in C++. Where have you seen that in C++?
Switch.
Switch, in a switch case, you have cases, colon. Does it execute it? Does that case execute? No, it's just telling you where to jump to. That's why a case switch is sometimes better than a lot of ifs, because a lot of ifs, you have to check all those ifs until you get to it. A case switch, it just jumps to that line. And that's why you need a break there to skip over the remaining, otherwise it'll fall through. So that's exactly what I'm doing here. So that whole principle of a case switch is very similar to assembly.
Wait, can you just explain the first line? Like, why are we starting with the BNE instead of?
Because, well, it just, if you think about it logically, it works. If I say they're not equal, then I want to do the else.
And that
Which
would
is,
go
because
directly.
that's what I'm saying. If I would do an equal, I could say that if they're equal, well, then what? Don't go anywhere. But that's what it's gonna do anyway.
Writing the else at the end of the command, that would just jump you to the else. You don't have to write J else.
No, it may be confusing you that I wrote the word else. I could have written here the word hippopotamus.
Yeah, I get
And then
that,
I could write hippopotamus
but
here.
I'm saying that writing the name of the label. And
Here tells me to go to here.
you don't have to write J, like.
No. Branch is a type of jump.
Mm,
It's
Gotcha.
not a jump. This is a jump with a J is an absolute jump. It means if you're at this line, automatically jump. No matter, don't ask any questions, jump.
So BNE.
But a BNE is ask a question first.
So it's the,
And it's therefore, it's called a branch. Branching means to the right or to the left.
the three arguments still are the two operands and then.
Yeah, notice that it's a B, notice that what's the encoding? Great question. What's the encoding of this? Well, first of all, it's an I type. How do I know it's an I type? Aside from the fact that I wrote it before, because it's got two registers. Anything with two registers is an I type. So this is an I type. This is the opcode, the two registers. What's this else? How is that going to be encoded?
The address.
It's going to be an address, right? It's going to be how many lines forward to jump, it'll be how many, it'll be actually a number. So therefore, how far can I jump forward? Maximum 32,000, which divided by 4, whatever. In other words, there's a certain, that same number, I only have 16 bits over here. So the largest jump I could make is limited by how much space I have in my BNE, which is 16. The jump, on the other hand, has a lot more space because there's only an opcode. And then I've got 24 bits of address to jump. So I can jump further with the jump. The branch can only jump me locally, which is okay because I use it for my if and else's. So that's usually local jumps. I'm not usually going to jump very far. When am I going to use a jump? When I have a function, right? Because I want to call some function that's way up in the code because everybody's using that function. So from all different places in my code, they want to jump there. So that's when I'll use a jump. In fact, if I have a branch and I want to jump far, what can I do? I can do a branch, and then at the line that I jump to is a jump. Right? I can say if it's equal, then go to this line. And this line, I'll have a jump there to go farther.
Is there a way to jump back? Is there a way to jump back once you jump?
Yeah, so actually I skipped that here.
Same way.
Yeah, you have to use a jump. It's something called JR, jump register, but I don't want to get into it right now. Where here, I mentioned this JAL. That's me. Okay. Really, you should do that in the lab. But
he does.
well, you will, he will, don't worry.
Oh, yeah.
We had one time. Really should be the lesson for the lab.
I think next level we actually have to do it.
Okay, look at this example. Here is a loop with a while. And
Loop start. Good.
that's just the label that I
Oh,
made.
that's the label. It's the label. It's true.
Now there's another command here, SLL. SLL is shift left logical. Shift, it means move the bits to the left. In other words, if I have 32 bits in my register, let's say I have like this. Let's say this is they're all zeros. And this is a 1 over here. If I shift it left by 1, then this 1 will drop off into the bottomless pit, and my register will be all zeros. If I had a 1 over, imagine it's 0 over here, but I had a 1 over here. If I shift it left, what's the value of this register now, first of all? 1. If I shift it left, what's the value going to be? If I shift it left again, what's the value going to be? Again, 8. It'll keep doubling. It'll keep doubling.
Finals.
Yes, it fills it with zeros. So it'll keep, so if I have a number, whatever number I have, if I have the number, here, what's this number? 5. If I shift it to the right, what will it be? It'll be 10. Because what will it be? It'll be 1, 0, 1, 0. That's 8 and 4. 8 and 2 is 10. So any number I have, doesn't matter what, even if it's an odd number, even number, any number, every time I shift it 1 to the left, I multiply it by 2. If I shift it twice to the left, I multiply it by 4. And that's exactly what I'm going to do over here. I shifted 2. That's the shift amount. That's the SHAMT. The shift amount, which we saw before. The shift amount, SHAMT or whatever you want to call it, it's shift amount. That's the 2 over here. I shift this 2, S3 2, and I store it in T1. Now, why am I doing that? Because look what I'm doing. I'm trying to iterate over an array. My I is going up by 1 every time. But since this is a array of integers, I don't want to go up by 1 every time. I want to go up by 4 every time. Now you could say, well, just add 4 to it every time. But the compiler doesn't know that. The compiler just sees this code. It wants to somehow capture this I equals I plus 1. It needs, as a compiler, it needs to sort of implement everything that you did. So if there's a I equals I plus 1, there's got to be an increment by 1 here. Look, here, see the 1 here? It has to increment by 1 because that's what I did. It can't change that to a 4. It's not like magically going to know that. So it has to do that because maybe, for example, I want to print that I at the end. Maybe the next line I want to print the I. I need to capture that fact that there's an I going up by 1 every time. So that's my S3. And then what I do is I take my S3 and I multiply it by 4. And then that's the amount that I put into T1. And then when I want to access the array, I go to T1 at location 0. So I'm sort of doing pointer arithmetic. Every time T1 is going up by 4, which means I'm going from the array place 0, array place 4, array place 8, 12. I'm going through the array, but based on T1. So T1 is kind of like representing how I'm getting through this array, how I'm doing this I plus 1, but I've also got this S1, S3 getting incremented by 1, and then I'm multiplying it by 4. Now this, it seems kind of like extra work, and it is extra work, but the compiler will compile it this way because he has no idea what your goals are. He just sees this line, I equals I plus 1, and he has to do that. He can't just ignore, he can't like figure out what your plan was. So he's got to have this line here. And then he's got to use that. He sees that it's over here. He's got to use that. And he knows that this is an array of ints. So he knows to multiply by 4. So he can figure this out. So this code is actually like a little bit circumloquacious. No, I don't know. It's like confused. It's a little bit complicated, more than it would be convoluted. There you go. It's a little bit convoluted.
Circumspect.
No, circumspect.
So it can't,
Circumloquacious. You know what that means?
Circumloquacious.
Yes.
I'm looking it up right now.
It means person who talks in riddles, kind of. He doesn't. He talks in circles.
Referring to someone who's using a text of language to evade a question.
that there's
Yes.
no, put it into,
Cool.
if you have a good compiler, you look at the static analysis, you see that there's no I after that, and it'll say, okay, we don't care about it.
You know, somebody could write some complicated compiler which would avoid this. But my point was, remember I mentioned at the beginning of the lecture today, that if you write in C, if you write directly in assembly, you can get more efficient code, really. And here's an example, actually, of him doing some extra work, kind of, to do this loop. And notice that I jump to the start of the loop and I go again. Where is my check for being finished while it's not equal to K? So I check as long as T1 has never as long as T0, the value that I actually have, remember T0, not the counter, this is kind of weird, while the value is equal to this, keep going. So as long as it's not equal. When
It's not equal.
it's not equal
Then you
and
exit, yeah.
and I exit, because that's the same thing as saying, as long as it is equal, keep going, the same thing as saying when it's
T0
not
is-
equal.
T0 is your
exit.
counter here, right? It's your, where you're holding your current value. Yeah, because that's the one we're checking against S5. Okay.
No, my counter
No.
is S3.
Okay.
My counter is S3.
Oh, yeah, T0 is your address near it. Okay.
She's,
Got it, thank you.
And
there's a BEQ and BNE. Yes.
so the Q at the end of the SLL, that is saying how many times to shift over twice. shift
Yeah, it's
over-
just, why did they do that? Because SLL is a faster, much faster way than doing, there's a command multiply. You could multiply by 4 or by 2.
No, can you multiply by 3?
You can multiply by any number you want.
Yeah, but that's the reason.
Multiply is by anything.
Yeah.
But in this case, I want to dafka multiply by 4. And it's much faster to shift. It's this command shift left logical will run through is a faster way of doing multiplication. It only works for doubling or multiplying by 4 or whatever, but it's much faster than multiply. Multiply is very complicated. We'll learn about multiplying. And you have to do, you have to do iterations to do multiplication. Question.
What's the second one? What's add on this word S6 is adding to C1? What is that? For 5, 4.
Because S4 contains the address of the first element. Yeah, because S4, sorry, S6. S6 is essentially a pointer to the array. Now, I need the address of the array, right? Every time I'm going to the array and I'm saying increment, go offset by I. So first I've got to get that address and add it to the offset. And that's the actualization I want. Right? Isn't that what I'm doing? What does this mean? This means take this address array and add to it the value I. And I keeps changing. So that's what I'm doing. I is changing. This is I changing here. Well, I is going up by S3 is going up by 1. And then I'm multiplying by 2. So ST4 is going up by 4 every time. But that's just the I. I need to get the address in memory,
Your first.
getting the first position of the array, and then add to it the offset, and then I get the value. So I got to do this over here.
Mr. Bubbles word.
Load word gets the.
Load word, once I've created the actual address that I want, I go to it with 0. Why is it 0 over here? What you really may be asking is, why don't I just put over here instead of, why don't I put over here S6 as the address that I want to go to, and then put over here T1.
Put a register there?
The answer is exactly your point. I can't put a register there.
Okay, that's fine.
Since I can't put a register there, even though I would love to, it's an I type. I only have 2 registers. I got to put a number. This is actually an extremely important point. I'm always going to put 0 there. Always put 0 there. And I just do pointer arithmetic. I just change them. I always go to the first location, but I'm incrementing where I'm pointing to in the array. So it's kind of superfluous. I'm just going to always have 0 there. If I'm going through an array, unless I want to jump randomly to the middle of an array, then it could be useful. But if I want to go through the array one by one, this will be a 0 always.
If you want to do a nested loop, where in the middle should we start them?
That depends on the circumstance, but somewhere probably after this or so before this, or I don't know. You have to. I have to. That's your problem. You got to work that out.
It's not like a fixed thing.
No.
It wasn't that crazy.
What's the most complicated mathematical operation you can do?
How you're I'm iterating over the loop to understand at what point you actually want to use the information up.
Professor?
Next.
Dynamically allocated into the corner thing. What? Oh my God, what?
All right. I don't want to do any more of this slides. I want to go on to the next. You can look at these slides on your own, or I'll be my.
He might.
He doesn't believe, he doesn't believe
in slides?
he doesn't believe in self-made slides. He believes in
He also doesn't believe in
in
shit.
using the book slide.
The book, but what if, what? That cannot possibly be the most efficient or best way to teach people.
Just check with- He's a good teacher. He's a good teacher.
No, I'm not saying he's not. Yeah, I'm
People
not saying,
made the book, hopefully theoretically people make the book or making it.
get out of here
Yes, slide.
with that stuff.
Wait, Dan,
No way.
I don't know what you're.
You guys want to be coming after Mr. Danzig.
I can't do first thing. What do you think about it?
I wrote comments on Moodle.
Oh, you wrote comments or you just hit it? Oh. Because I really.
But
enjoyed
I
that.
generally basically like them, and I basically say great, and then here are the things I didn't like.
Unless you're.
No, I got. I thought I really popped off. It was really fun time.
Basically, all the grades were pretty much between 90 and 100. So I just like, I was debating, like, should I give a 93, 94? You know, that kind of thing. Because basically my attitude is that, you know, hopefully you, if you know English, you should get a good grade in the class.
From my website, I thought that was quite funny. Do you see the picture I put my brother holding my own child and saying he's a single father? Did you see that one?
I don't, actually, I don't remember. I'm surprised, but I don't recall. Okay, so let's start, and now we're really in, that was enough for the language, now we're really into the architecture. So, running commands in MIPS. Each command must be stored in the processor's RAM. In other words, all the program, actually better, I should rewrite that and say the whole program must be stored in the computer's RAM. But we can't run the program directly from the RAM. I mean, we do run it from the RAM, but we have to copy each single line one by one into a special register called the IR, which is not here. But there's a special register called the PC, which contains the address of which command to be executed. You know, it's not each command must be stored in the processor. It means the whole program must be. And the program counter, imagine the program is like a set of lines, line, 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 line. And the program counter is pointing to a particular line to execute. When you do a jump, then the program counter jumps to that location and points to that place. So the program counter is a register which has an address of which line next to execute, the next line. When I'm executing line A, it's pointing to the line B, pointing to the next line. Before the execution of this command, the PC is incremented by 4 so that it points to the next command before executing. Assuming there's no jump. Assuming, or pretty much in a normal case, I'll always increment it by 4. Because that's the way the program is going to go through my lines of code. The whole program is in RAM, and the PC is just keeping track of where I am in the code. It's kind of like a place marker in a book, so that you know which page you're on. Question? Your question?
Yeah, if I exceed 1 billion lines of code, will that be a problem?
If you what?
Because the register PC only holds 2 to the 32 bits. And if it increments by 4, that's like 1 billion lines of code that I have.
Yeah, it was super limited.
Oh, instead of 4 billion, you mean?
Yeah.
No.
Oh.
Sorry.
Yeah, that is a problem. But since so that's a good question you're asking, saying like, it's only 32 bits, but like you're saying, what you're saying is the first two, the rightmost bits will always be 0, 0. Because it'll either be line 4, line 0, line 4, it'll never be line 1. It'll be the 0, 4, 8, it'll always be increments, because every command is increments of 4. We're always gonna be on a word boundary. We're never gonna be anything else. So once we get, so then we can only get to
25% of our.
we only get 25% of the possible places in memory. The answer is no. What we'll do, one possible, can anyone think of a solution to this problem?
You increment every time, like.
What's the problem?
Missing code.
Yeah, that's a good question, but really, it's, we'll get to it later. But it sounds like this. If this is my 32 bits of my PC, well, let's say I'm pointing to line 0.
then they'll all be zeros. Let's say I'm pointing to line 4, then it'll be all zeros, and what'll be here? It'll be 4, right? It'll all be zeros.
No, but you can have multiple.
And then it'll, if I'm pointing to line. Wait, how,
You just
what's
pick
the
which
flaw-
byte.
what's the largest value that I could have there?
The 32. No, what, for the 32-bit PC?
Well, the largest value I could have there would be all ones. And then 0, 0, right? Which is what?
4 billion minus.
4 billion minus 4. Wouldn't it just be 4 billion minus 4?
It's a little over, it's still over.
It actually gets everywhere. I don't see a problem.
Okay,
You see what I'm saying? I still can get to the last place. It's actually not a problem. The last place,
No, it's not, it's 4 each time though. It's 4 more, it's 4 possibilities you don't have for each number. Well, 3 out of 4.
but that's okay because how many,
You also get a specific byte.
doesn't matter. I'm never gonna go to a byte in the middle. I'm always gonna go, I'm saying, what's the highest byte that I ever want to go to? Highest 4-byte word that I ever want to go to, that, and I can represent that. I can, it's not like I don't have any limitation.
so it's not that every fourth,
Oh, okay.
we can only use every fourth byte, it's that the lowest. No, it is.
If I can get to 0, I can get to 4, and I can get to 4 billion. This is 4 billion.
But you can't get to 1, 2, and 3.
Yeah, but I don't need to get to 4, 1, 2, and 3.
That's the only thing you have to.
No, I could get to them, but I never will.
In the middle of the word.
Okay.
Yeah, it doesn't even-
It doesn't matter. I would never, exactly, I would never get to there.
Why is it 4 billion by minus 4?
Well, put into your, go into Google and type 29 ones, and then 2 zeros. And ask it to calculate it what it is.
In binary.
No, I'm saying, but why would you 0 the point? Why are they all ones?
29.
Because there always is gonna be 2 zeros on the right, because the lines of code are always at increments of 4.
So it's always gonna be another one moved in 2 by 2.
What's 29?
It's like shifting again, like the SRO.
Here, let's.
Yeah.
Let's
it's 1
do it.
billion.
Do the architecture.
Like, if you're writing something in assembly,
Not a billion.
Oh, I thought you were just gonna put. Are we doing it? We doing it? I like gravitate. Yeah, we're good. Do it. Do it.
Wait,
So-
you could just use your calculator, 2 to the power of, and you get like 1 there.
Wait, what does this mean? Oh, yeah, so like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25,
Why don't you just think of the power of 10?
9, 30, 30, 31.
130.
10 million.
What? Decimal? Oh, here. Is that right? That's only 2 billion.
Wait, only 29 and not 31.
how many ones are there?
10 to the 9.
I don't know why.
That's only 2 billion.
1 billion.
What?
Wait, only 29.
I maybe I never had enough ones?
No, it seems at the bottom you can see.
Why it's 29? One is the third.
How many ones did I write here?
Yeah,
29.
You have 29, so that gives you 2 to the 30th. That gives you 2 to the 30.
Let me do that again.
I think you're gonna add a 1.
1, 2, 3, 4, 5, 6,
Add a 1.
9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. You're right, 30, 31, 32. That's
No.
And now I can convert and I get 4. So I get all the places.
And then -4. That's cool.
That's in 2 copies.
Yeah.
So
Wait 1 second. It's really 2 to 32.
you see, I can get to all possible places.
It's 2 to 32, no?
Alright, guys, quiet it down.
2 to 32 possibilities, right?
Okay, please be quiet.
But like Tara said, there's a limit to how many lines.
So there's no problem, there's no problem. Okay, a word about hexadecimal. In this course, we need to relate to bits of binary, to bits of binary numbers. Sometimes we'll write the numbers in binary, but sometimes it is more convenient to write a hexadecimal because it corresponds nicely to binary. Every digit of, this is a very important line. This is the second thing you have to know. What was the first thing I said? That a byte is 8 bits. This is the second thing. every digit of hexadecimal corresponds to exactly 4 digits or half a byte of 4 digits of binary. So for example, I can write AC, the 0x just means it's in hex. AC, I can just say A is 1 is 10, so that's 1 0 1 0. And C is 12, that's 8 and 4 is 12. So I just can write it part by part. And then I can immediately convert from binary to decimal without, and here's another example, F2. Well, F is easy to remember, it's all 4 ones. And 2 is obviously 0 0 1 0. So that's F2, so I can write binary in a faster way. Okay,
It's the quick conversion pixel.
oh, this is the I format, we already saw this. But let's talk about it again. Remember, there is 6 bits, 5 bits, 5 bits, 16 bits, a little bit off here. I is for immediate. We said that the last 16 bits can contain an immediate value and offset.
Well, what does immediate mean? I don't understand.
It means that the
It's a hard
Ins-
code.
exactly, it means hard coded in the instruction, as opposed to a register, which I then have to go to the register and see what's over there.
It's what we're not allowed to do in Word.
So
Nice.
the largest value, the address offset now should be within plus or minus 2 to the 15 or 32,000 bytes. So in other words, if I have a branch, I can jump 32 plus or minus 32,000 bytes. Based on the value of the first field, MIPS can know which format to expect. Right. MIPS will know, or the compiler will know, if I see if these opcode there of 30 of not 0, then it knows it's an I type or a J type. Okay.
And 0 is an R type.
The offset immediate field contains a 16-bit number in the 2's complement method. If the opcode field is different from 1, this is another point we should discuss. If the opcode field is different from 1, then each value of the opcode specifies a different command of the I type. But if the opcode is 1, so now we're explaining something special. We have an I type where the opcode is 1. So then there are several possible commands. The command code is listed. The command code is listed in the RT field. You hear this?
What?
This is another complication.
Why?
If the opcode is 1, and then you have to go to the RT to find out what command it is. You understand?
No.
All these slides are on Moodle.
What does open code 1 mean?
Opcode.
The opcode.
Op. In other words, here, the op here. If this is a 1, then you got to look over to the RT to find out what the command is. Well, I'm making it right now. I'll put it on Moodle. It's on Moodle. Moodle. Hopefully it'll be automatic. I'm now recording and hopefully it'll be there.
I don't. We said that the opcode is add.
Guys, you make too much noise in the back. Give respect to your fellow classmates.
So the opcode is whatever the commands that we're giving to that line. Right?
The opcode is the way of defining what the command is.
Yeah.
If it's 0, it's an R type. If it's not a 0, then it's either a J or an I type. And if the opcode is specifically 1, then it means look at the RT field, and that will be now the opcode. This is like a special, basically what happened is like this. They had all their commands and they wanted to put some more in. So they said, well, 1 will give us some new space now, we can use this. But then we've already lost this. So guess what these I types are going to be? These are going to be only 1 register. They're going to be 1 register. So we invented now a new type, which has only 1 register. And here are some examples of them. For example, branch on greater than 0. Branch on greater than 0, what is it? If you think about it, I don't need only 1 register. It just means if this register is greater than 0, just checking it always against 0, so I don't need to write the 0. If this register is greater than 0, then go to this location in the immediate field. So similar to this, branch greater than equal, branch on greater than or equal to 0. This is greater than 0, this is greater than equal. This I'll skip for now, but branch of less than 0 or less. So it's always been related to 0. Now, if I want to check if a value is positive or negative, I can use these commands, and then I have like it's sort of a shortcut because I don't really need it. I could just use the branch equal, and but or it saves me a couple lines. It saves me 2 lines instead of 1 line instead of 2.
Are they
does
both
zero
written
and
in
link?
capital? Or are they just there for?
The case of the uppercase, lowercase is not insignificant for the name of. You could write add in all capitals or in all lowercase.
Which one is, what is BLT's all?
These ones I said I'll skip.
Okay.
We'll talk about that later. The load command. So this is sort of a review of things we said already. The load command loads a word size datum from the memory into a register. The format is just getting used to this style of format. The format, guys, I don't like to talk over you all the time. I'm talking for a long time. I teach a lot today, and it's hard for me to talk, but everybody's talking. The load, I try to ignore it, but at a certain point I can't ignore it. The load word command is takes an RT. See this style of writing? I just want you to get familiar with this style of writing. This is the way you'll see a command in the MIPS green card. You'll see, this tells you the RT is where this is very useful because it's telling you that the RT is where I'm loading to, and the RS is the address of the array, and that's the offset. The action is summarized in the following manner. RT equals the memory, what's in memory at location offset plus RS, right? That's what I'm doing. Taking the RS, adding it to the offset, and taking that memory location, and the value that place is going to RT. This is just review of what we've already done, but this is to understand the notation style.
Yeah, like load as in load word key, like what we
This
saw.
is load
where it's
word.
Loading this location of memory plus this register, like to find its exact location.
The offset combined with this address will be the actual location that I want to store.
What's the RS here? That's the.
Remember, in the format, there's an RS.
Oh, the RS is the.
This is
second
the
one.
there's the RS and the RT. So it's actually telling you
So
which
what's
one.
the offset there.
This.
Got it. Perfect.
Explanation. So there's an explanation. Offset must be. The offset must be sign extended into sort of basically I'm going into detail now about the same things that we talked about. Before we talked about it from the viewpoint of a programmer. Now we're getting into more details of what the hardware is going to have to do. The offset must be sign extended to a 32-bit address. So what do I mean by that? A normal address is always going to be 32 bits, but our offset only had 16 bits. See, it's only 16 bits for our offset over here. So we have to fill in, we have to create a 32-bit address. So we're going to fill in on the left an address that's proper, which means if it's a negative number, we'll put ones there. And if it's a positive number, because remember, when we jump, remember jump, we're at a branch, let's say, or load word. Load word could, we never did this in C++, but in load word, you could do something, which is you could say go backwards. In other words, I think you can do it actually, but we never tried it. But you can make an array and say go to offset -3. Normally you do always the offset is positive, right? But you could do a negative. And then it would go upwards, right? You could do that. So the same thing here. The offset of a load word could be positive or negative. Because I could be pointing to the end of the array and I want to go back now. So it could be positive or negative. So I have to sign extend and extend it, but with the sign. So if it's a negative number, put ones there. If it's
16 ones.
16 ones.
Seems so obsessed.
I gotta fill in the thing. Or if it's positive, then 16 zeros. So I'm just explaining what's written here when it says must be sign extended into a 32-bit address. For positive, we put zeros. For negative, ones are placed in the upper 60 bits. The offset now indicates the number of addresses to jump to. The processor, which is the computer, adds the contents of the RS to the newly extended offset Now we have an absolute address in memory, which we want. Now, as absolute means we have the actual address of where we want to go. The contents of this address, are transferred to the RT. For example, and here's an example, load word 32 at 3 into T0, register number 3 plus 32 into T0 becomes, the way you would write that is T equals memory location of 3 plus 32. Just showing you sort of notation. Another example of an I type is the store instruction. So we saw this already. This command stores a given piece of data located in register RT to a memory location indicated by RS. The calculation of the address is the same for the LW. As we said, after calculating the address, the processor transfers the content of the RT, the register, to the memory address calculated as above. So that we already know. For example, this is the store word, and this is what we say. We say the address goes into memory at that location.
Can you go back to that for a second?
In other words, this is what's getting the value of this, because it's a store word. This is going, remember I said the arrow points to the right?
Yeah.
So the way we write it is we say memory at 100 plus 4.
What is this code doing?
This is just sort of like scientific notation of what we've already explained to you. It's just teaching you that this is the way we'd write it. It's so, but we're going to get to some other commands. We're going to learn some details about it. The third type of I instruction, branch. So now we're going to talk about branch. This is a little bit new here. Branch instruction compares the contents of 2 registers and performs a conditional jump, right? Branch equal, not equal. It compares 2 registers, and then depending on whether it's an equal or not equal,
It only
jump.
does equal, not equal, not like greater than or.
It only does equal, not equal.
Equal, not equal, what?
So for example, branch equal RSRT, go to offset. The BEQ directive means compare if there is equality, jump to the different line of code for execution. The jump may be forward or backward. It is relative to the current location. That's a key point. It's relative. It's not like a regular jump, which is a jump is saying go this absolute location. This is a relative. In other words, it's saying jump forward, jump backward from where I am now. How are we going to do that? How do we know where we are? How do we know where we are? So the answer is the PC is keeping track of where we are all the time. The PC is always actually one step ahead of us. It's always the next line that we're about to execute. So I can look what I can do. So here's the technical definition of the BEQ. If RS equals RT, then the PC, what does jumping mean? Jumping essentially means changing the PC. Tell us that a PC shouldn't be here, it should be 10 lines down, or it should be 10 lines before. Just change the PC. So actually what I'm doing is I'm changing the PC to whatever the PC currently is, plus the offset, but the offset has to be times 4, because the offset will actually, this is going to gain me some space. Now the offset will be up to 32,000, right? But if I multiply it by 4, then it gets me up to 128 or whatever, some other larger number.
I thought we were to hold 32,000.
Yeah, but I can use, but every bit can be significant. In other words, since I'm always going to be jumping to something that has 2 zeros at the end.
Oh, so
Why bother writing them?
Ah.
This is a key point in engineering
It's pretty
here.
much just adding that.
That's
on
what I
the
was
end.
now since we're always going to have 2 zeros over here,
You might as well.
let's just not bother writing them. And then we'll just write just this part. We'll write the jump to just 16 bits. We've got 16 bits that we can take. So we'll take these 16 bits, ignore these. Of course, we can't have more than 16. We'd like to, we don't have space. So we'll take the 16 and then we'll multiply whatever the machine will do this. The machine will take the PC, add the offset, but the offset first multiplied by 4. So that will, right, this is like parentheses here. Offset times 4. You don't need parentheses because of order of operations, but
Just moving to the left twice, right?
exactly, move to the left twice. So the machine will do that multiplied by 4. It'll essentially append 2 zeros to it, and it'll get an 18-bit address. You see what I'm saying? It'll get an 18-bit address instead of a 16-bit address. It'll also actually have to sign extended. right? In order to add the PC, you can't add 32 bits to 18 bits. So it'll sign extended also. So it'll be 32 plus 32. And it'll get a 32-bit result and copy that into the PC.
But when we actually use BQ, for the last argument, are we putting a number as the offset? Or we're putting a name?
Yeah, you gotta switch gears. We're switching gears in this course now, very dramatically.
Okay,
Up till now, we were programming.
Yeah.
And then in the programming, you just write your label. You just write branch to exit. But now we're talking about what's going on in the hardware. What, for programming, no problem, just write exit. I don't have to worry about anything. But over here, I have to understand what's going on in the hardware, because that's what we're gonna be analyzing in this course. What exactly is going on down inside? And what's going on is that the offset that was given to us has to be shifted over. So actually, if I ask you what the encoding is, it's like this. If I want to jump ahead, let's say I want to jump ahead 2 lines. Okay. So what am I going to write in my branch? In my code, I'm going to write BEQ, I don't know, $T0, $T1, and then I'll write, if I want to go ahead 2 lines. Well, what will I write?
lines in the code?
2 lines in the code. So I'll actually write 2 here, even though I really want to go 8 forward. Even though I want to go 8 bytes forward, right? Because the 2 lines ahead is 8 bytes forward. Actually, I'm not going to write 2 here.
So you like,
I'm going to write 1 here. Why am I going to write 1? I want to go 2 lines ahead. That's my goal. My goal is if they're equal, go 2 lines down.
so.
What am I going to have to, what's the encoding going to be? I'm going to write a label here as a programmer. I'm just going to write, line, exit or line start or whatever place I want to jump to. But what will the actual encoding be? It'll actually be, if my intention was to go 2 lines forward, it'll actually be 1. Let's explain why. Now I'll explain why. I didn't explain why. Because first of all, the PC is already pointing to 1 line forward. I don't want to go there. I want to go 1 more than that. So that's 1 more. And I know that it's going to take this 1 and multiply it by 4. So this 1 will actually turn into a 4. So 4 plus PC plus 4 plus, that'll get me 2 lines ahead. So the encoding, this is a key point, and this can be a test question. What is if I want to jump 2 lines ahead, the encoding will be 1 over here. If I want to jump 3 lines ahead, the encoding will be 2 here. You see, it's actually convenient because the number of lines that I want to write, I just write 1 less than that. But if I want to go backwards, what do I want to go backwards 1 line? So then I have to, you see, I'm already ahead of 1 line, so I got to go minus 2. If I want to go back 1 line, I got to go minus 2. Well, I'm already ahead.
Because of the PC.
Because of the PC being incremented already before this is executed.
That's interesting.
Okay, so the PC is the following instruction address. The offset is multiplied by 4 and then sign extended. That's what I said, to a 32-bit number because we can't add the PC. You can't just say PC plus 4 because this is 32 bits. We got to turn this 4 into 32 bits. And as we got to have like size numbers. Okay. So by the way, that was an engineering trick. We squeezed in 18 bits, if you think about it, into 16 bits of space. Because we dropped and because we always know that we're always going to jump in increments of 4, so we can drop off those zeros and we get a little extra distance. And that's always the goal, right? If you ever watch Apollo 13, great movie. You see how engineers try to get more out of something.
Do you think we could watch it next week? Is that
Instead
good
of
use of
class?
class time?
No.
Not instead.
Or
class.
What?
I have a question.
Yeah.
So we're saying that we can put 18 bits onto 6.
Well, I was speaking poetically.
Yeah, the thing is that how does the computer actually know that? Because
No, the computer is built. It doesn't know that, but whatever it sees there, it's going to multiply by 4. If you write a 1 there, it's going to think you mean 4. If you write a 3 there, it's going to think you mean 12.
But how does the computer understand that if it's only understanding 1s or 0s? So how does the computer actually know that
It doesn't understand. It just does that computation. It just multiplies. It doesn't think. It just whatever number is there, it multiplies by 4. Always.
Whenever an R is,
That's the way it's built. It's built to do that.
Whenever-
That is its
you
functionality.
said whenever an R is there, it multiplies by 4?
It's like in Star Trek, instead of they ask the computer to do something, and in the old Star Trek, and they would say like, that is not, I'm not programmed to do that, I can't do that, that's just something I can't do, I'm not programmed to do that.
So you said, when does it multiply by 4 automatically, when an R is given?
Yeah. All right, what, when an R is
Wait.
given? No,
I'm saying when it was,
Well, you just told him that it automatically multiplies by 4.
that's what we just explained, that anytime you do a BEQ,
Or B.
it's gonna take,
Okay, sorry, thank you.
the 16 bits and multiply. By the way, that's not the case by a load word. You see, why do you say by the load word? We'll also multiply by 4. Every time I'm doing a load word, I can multiply by 4, so it's 4.
So what's the difference?
oh,
The difference is because the hardware for load word is the same hardware as load byte. And if it would, and if it would always multiply by 4, then I would never be able to do a load byte. Because it would always jump by 4. I want to be able to get, but load byte by definition, I want to get anywhere I want to get. So if you're always going to be multiplying by 4, then I'll never be able to get to 3 or 2. I'll always be at 0. So, so we could have done it. We could do it, but then we'd have to have separate hardware for a load word and load byte. So we don't want to do that. We want to have the same hardware for load word and byte. So therefore we lose something. We're going to have that we don't multiply
For load word.
for load word.
Okay, but we do for.
But for this one, it's
BEQ.
different hardware anyway. It's different root.
Okay.
It's a different, what we call a different data path. And in that data path, we'll always multiply by 4.
Wouldn't-
All right, I guess we'll stop here. Next time, we will do the in-depth discussion of the jump command. And I suggest, well, complicated, anybody? There is homework, actually. Let me stop.
Wait, we have labs and homework?
No, it's pretty bad because there is homework.
Is homework due every week?
And